Hi, Gavin, everyone. Okay, so we've just introduced this idea that spontaneity, or the likelihood that some reaction is going to go forward without constantly having to keep it rolling with an input of energy, is related to this quantity called entropy. And entropy is related to the number of possible states that a system can take. Or if you like, it is the dispersion of energy throughout a system. So anything that allows energy to become more diffuse rather than concentrating in one place is just more likely to happen. Um, so we talked about these microstates quite briefly. There is a way, or quite a specific way, we can relate entropy to the number of microstates, and that's through Boltzmann's equation. So entropy is equal to some constant, Boltzmann's constant, times the ln of the number of microstates, which is usually an ohm, okay, in the first kind of formulation of it. Now there's also a statistical mechanical formulation that takes it as the sum of all of the possible microstates, but that's really outside of our lane for a 101 class. But if you're interested, go ahead and look it up. And what does that mean? It means that if atoms or molecules or gases, for example, can take up more space and occupy more different ways of organizing themselves, they will. If you read through your sheet, we're looking about gas opening up into a vacuum space. Are the gas molecules likely to just stay in their own space once that stopcock is opened? Or will they expand to fill the entire area? You're increasing the entropy by increasing the volume that they can take up, so it's going to spontaneously expand to fill the space. Even though it's not impossible that all of those gas molecules are going to find themselves back in one side, the chances of it are so low that it never happens in practice. And remember here, we're only looking at kind of a model system of what is that, like maybe a couple dozen atoms. If we were looking at two gas molecules, what are the chances that both of those gas molecules will be on one side or the other at any given moment? It's not zero for sure, and it could be calculated. But if we go up to three, now what are the chances of getting all three onto one side, or four? Or what if we get a mole of gases? So when we go up to that many molecules, the chances of them all going to one side at the same time are so slim. They're practically zero, and we never really see it in practice. So that's kind of like for the bulk scale thinking of things, and that's kind of why I find the physical chemistry of nanosystems, where we really are just talking about a couple of molecules again, to be really interesting, and why I say that scale and those sorts of systems are really the best of physics and the best of chemistry. But hey, that's just my personal bias. Okay, and you can keep reading through the handout, but really that's just things for you to read. Okay, so entropy and changes in heat. How does heat and things that we've already talked about in the course relate into this new concept of energy, and how can we relate them to one another? Because again, one of the goals of thermodynamics specifically is to try to relate these state functions like pressure, volume, temperature, internal energy, and now entropy, as well as the other ways of measuring energy use, so heat, work, into a coherent system where if we know certain quantities, we can calculate the others. Okay, so for a gas that is heated, so here we're looking at this mole of neon. So this is going to be heated, and usually when you see the word reservoir, think it's so big that it doesn't matter how much energy it's putting in. The reservoir is not going to change its temperature or the amount of heat. It's just going to be negligible change there. But we are heating up this mole of neon, and we're going to heat it up to the point that it's going to do exactly as much work as the heat going into it. So this is what we would call a reversible change, meaning that we could put in the work that's going to press down on the plate, and the exact same amount of heat would then leave again. So the work or the energy that's exchanged going in is exactly the same as though we were doing it in the opposite direction. And the change is so small and incremental that we're not losing anything to friction or to just waste heat. So this is not a system we could build in real life. We're always losing energy to friction, to waste. And that's just the cost of doing business in the real world. But we do end up, we do get some useful quantities or ways of thinking about it when we look at this. Well, what if the heat going in did exactly that amount of work? So one of those is that the change in entropy of the system, and we're going to return to this eventually too, is the reversible heat gained by the system divided by the temperature. So this is the heat absorbed during this reversible process per temperature that it's at. So at a lower temperature, the heat coming in is going to do more or have a higher impact on entropy than at, say, a very high temperature. Then it just won't have as big a change in the entropy. So that's kind of these reversible reactions. Again, don't think of it as a physical thing, but it will come up, especially if you stick along with either the chemistry or physics tracks. We're going to see these reversible ideas again, okay, as kind of like an idealized work. But it lets us takes us right into the second law of thermodynamics, which is the law that's going to define entropy for us. There's a bunch of different ways, really, of phrasing this law in a same way. But one of the earlier and simpler ones is just to say that that energy transfers from a hot thing to a cold thing. That energy transfers spontaneously from hot to cold and not from cold to hot. Something is not going to spontaneously become colder while spontaneously heating up another thing beside it. However, something that is hot relative to its surroundings will give up that heat to the surroundings. So again, a cup of coffee that is hot and allowed to just come back down in temperature to room temperature, it will spontaneously release its heat into the cooler environment. The cooler environment will not spontaneously heat up that cup of coffee. At least I haven't seen it. Although the environment is certainly holding enough energy to be able to do that, it's just not a spontaneous process. So that's really what this is saying, that there's no device that can transfer heat from a colder to a warmer reservoir without a net expenditure of work. So this is the idea that we can't even separate the hotter from the colder gases that are in the air without doing some kind of work to separate them. Also known as Maxwell's demon. So in that idea, if we had just a box with a little trap door in it, that, say, if we had a bunch of hot, fast-moving gas molecules and an equal number of cold, slow-moving molecules, would it be possible to just trap all of the cold ones on one side and all of the hot ones on the other side? So that would be spontaneously making, say, this side, if we want to push all the cold ones over here, cooler. We couldn't do that without, and I guess I should use the red pen, without some little fella sitting up there working the switch. And this is Maxwell's demon. That there has to be something providing a source of energy in order to be able to make that differentiation, or else how is it going to tell whether it's a hot or cold? And the most practical use for this is to think about changing a piece of memory in a computer from 1 to 0. That switch even itself takes a little bit of energy because you are changing the state of the system. So nothing comes without cost. And that cost really is just a waste. What we call waste energy or it's energy that can't be put to useful work. And that, like I said, is just the cost of doing business in reality. And that's where we say that the change of entropy of the universe is always rising on average, even though, like I said, for just like a couple of atoms, yeah, we can get away with it. So it's not always the case, but on average, it is the case. Another way to state it, yeah, it's just that. So all real processes occur spontaneously in the direction that increases the entropy of the universe. And I've already written that down, so I won't rewrite it. Okay, and moving quickly on, we'll talk about our last little quip for this video, and just a quick statement of the third law of thermodynamics, which should make complete sense to you now, even though this phrase probably didn't mean anything to you when I started this video. So a perfect crystal has zero entropy at absolute zero. Let's break it down. What does a perfect crystal mean? So we're looking at some set of atoms that are absolutely perfectly aligned, not like my drawing at all, that can't move from that alignment. Okay, so we're going to imagine that those are absolutely square and every direction in here is exactly the same. So here is our crystal of 16 atoms, and it's at absolute zero. So that means that there is, all of these atoms are not holding any energy at all, right? They're not vibrating, they're not shifting in accordance with each other at all. They are absolutely and perfectly still. So if they are perfectly still and perfectly aligned, there's no movement in it at all. And there's only one way of doing this. There is only, if I moved any one of them out just by a little bit, that would be a completely different microstate. There's only one way to get these 16 atoms in this arrangement and keep them absolutely perfectly still. And so because there's only one microstate, and entropy equals Boltzmann's constant times ln of the microstate. What's the natural logarithm of 1? Entropy is equal to 0. So here we say a perfect crystal has 0 entropy at absolute 0. So it's really just a restatement of the same thing. Okay, and as the temperature increases, now we're getting these atoms to move slightly. They have more microstates that they can take. So as the temperature rises, entropy rises. What else have we got? Kinetic energy. So the energy, what we've also called the internal energy, is going to go up, or kinetic energy. And of course, this goes through because the number of microstates is also going up. Okay, when changing the physical state of the system, we said that in the last video, we're saying it again here too. If the physical change, so whether it's dissolving a salt into ions or a metal into ions, whether it's turning a solid into a liquid or a liquid into a gas, or all of those processes in reverse, if it's increasing the freedom of motion of the constituents of the system, then it's also increasing the entropy of the system. Okay, so that's the second law of thermodynamics, and the third thrown in for free. And if you forget, there's also a zeroth law of thermodynamics, which we didn't mention here. And all that's to say is that if object A is in contact with object B, then they are in thermal contact. Heat can flow between these two things. And if object B is also in contact with object C, then object A and C are also in thermal contact. So heat can flow from A to C, or from C to A, really just depending on which one is the hotter object. Okay, so that's going to be it for now. Thank you again for watching, and I will see you next time.